Hello, in this course we have been looking at different techniques for preparing nanomaterials, usually in the context of some particular application or some particular property that we are trying to investigate. In the context of that property or that investigation, we have highlighted any challenges involved in making those kinds of samples and how those samples can be utilized. So, in today's class we are going to do something slightly different. We are going to focus on an approach to prepare bulk nanostructures. So, actually in fact we did look at one technique earlier which had some capability of this nature, but here we will focus on another technique which is particularly useful in the context of making bulk nanostructures. So, our learning objectives are first to understand the need to create bulk nanostructures. Again, this is something maybe touched upon briefly at different in different classes, but we will see that for the sake of completeness here. Look at some challenges involved in trying to come up with these kinds of bulk nanostructures, and then finally look at this particular technique called plasma spray technique. So, that is a particular technique which helps us do this, make nanostructures sort of in the bulk scale, and that is what we are interested in. Okay, so what is the need to create bulk nanostructures? Well, first thing is there is like a scientific need and a technological need. So, this is the scientific need. So, the scientific need is that we want often we want to do material synthesis and processing, and then we want to look at the properties of the material. So, we have many techniques that are readily available which help us study study properties of materials. The only issue is that those techniques have evolved over the years and they have typically been used for bulk samples. Techniques available more readily suited for bulk samples. So, this is the issue here. We have techniques that are readily available in the marketplace or in our labs, which are typically intended for bulk samples, and it could be any property. It could be a range of properties that we have already seen, some other property that we have probably not looked at in this class so far, but almost always we have this situation. So, if you suddenly say you have made a nanomaterial and you have made a very tiny sample of a nanomaterial, then the chances are that even though you have the technique available in your lab, that instrument that you have will not be able to probe this particular sample, because the sample size is very small, and it may want sample to be in a certain geometry, it may expect the sample to be of a certain size. The instrument will have some sensitivity. It will say, let us say it is applying load, for example, it will say that it can put in terms of a load so many newtons it can put. And then minimum it will have a minimum value for the load it can put and a maximum value of load it can put. Therefore, it will require your sample to be of a certain size, so that that load will correspond to a certain value of stress, and therefore, you can do a mechanical test. So, now if you say that I do not have a sample that size, I have only a sample that is 1 millimeter by half a millimeter across, then essentially even though you have the sample and you have the technique, you cannot make a measurement. So, that is a problem. So, one of the options that people have then is to come up with new techniques, new instruments and techniques So, one approach would be then that you have to create new instruments and new techniques to handle nanomaterials, but then you have a problem here. So, you are going to spend a lot of money and you are going to keep on having multiple versions of the same technique. So, let us say it is hardness tester, you will have like 2 or 3 different versions of the hardness tester depending on the size scale you are dealing with. Conductivity measurement unit, you will have again multiple sample holders. So, you keep having to keep on building up infrastructure to test a range of samples simply because the sample quantity is small, sample size is small and so on. So, from a scientific perspective, this is an issue that if you work with small amounts of nano samples, nanocrystalline samples, it is inconvenient to you. Therefore, if you are able to make a slightly larger sized sample of a sample that has this nanostructure in it, then you can actually do some scientific testing of that sample using techniques that you already have in the lab. Now, it is not simply about the need to keep buying new instruments, it is also about repeatability of results, it is also about comparing data. So, I can do a test on a macrocrystalline sample, I can do a test on a microcrystalline sample. I would like to do the same test on the same fixture with the same operating condition on a nanocrystalline sample. Then I have greater confidence when I compare the data. When I compare the data, I have much greater confidence that there is no instrument effect that is hidden from my considerations that I have missed in some sense, that is now clouding the data of the nanocrystalline sample. So, it really helps for a very thorough scientific study to have samples which are nanocrystalline, which can also be tested on instruments that are meant for larger scale samples. Therefore, there is a need to create bulk nanostructured samples from the perspective of scientific activity. This is an industrial activity. Making usable products is an industrial or technological activity. Okay, so this is an industrial or technological activity, and again there also it makes sense. Let us say you have tested something in the lab and you know that the nanocrystalline version of that particular composition, that particular crystal structure gives you some really interesting property which you will not otherwise get. And let us say you want to use this in some let us say you want to use this in a drill bit, let us say you want to use it in some nut and bolt arrangement that you have made. You want to use that for a rim of a spectacle that you are making, any number of things. Let us say it is supposed to be the heat shield for a spacecraft. Any number of applications, they are all macroscopic applications. You have something that you are holding in your hand, you are bending it, you are putting it on some location, lot of things you are doing which is macroscopic. So, again it does not help if you have seen some property in the nanoscale, but you cannot make a large sized structure in the which is large externally overall dimensions wise, but if you look at it in the microscope it is nanostructured internally. So, therefore, there is a very strong need to make bulk nanostructures both from scientific perspective as well as technological applications. So, what are the challenges involved? Why is this such a big deal? Why should we bother about it? First thing is control of surface composition. So, this has got to do with reactivity. As you are aware, every time you reduce the crystalline size, you are increasing the number of unsaturated bonds at the grain boundaries. More grain boundaries, so more incomplete or dangling bonds. So, therefore, any nanocrystalline material by nature is very reactive, and so even particularly during the synthesis process where maybe you are under temperature conditions where it can more easily react with various other constituents, you can create a situation where you are trying to make a bulk material of a certain composition, but what is formed is a bulk material of some other composition, maybe it has got an oxide layer or some other such thing is happening. So, control of surface composition is a challenge which you face when you have nanocrystalline structure as opposed to when you have microcrystalline or macrocrystalline structure. Boundaries between particles. Again same issue, you have you want continuous boundaries, and you want compositional control. So, you want the bonding between the particles to be very strong, so that it comes across as like a continuous material, continuum should be there, and you do not want an oxide layer in that boundary, so to speak. So, this is a situation that you have to face. Uniformity. So, this is uniformity even let us say sample to sample. In any even in a scientific activity, we normally say that how many samples have you tested, do you have 5 samples that you have tested, do you have an error bar with respect to those 5 samples, what is the mean, what is the standard deviation with respect to the property that you have tested. So, this is a requirement. This implies a certain uniformity in that sample, that sample to sample you have that level of uniformity, and therefore, if you are making tiny quantities of a sample, there is a greater chance that this tiny quantity that you made today is slightly different from the tiny quantity you made tomorrow, and so on, and therefore, uniformity becomes a challenge. The smaller the sample that you make, the greater is the influence, potential influence of the surroundings on that sample, and therefore, much higher level of control is required. So, this is also important from I mean from a scientific perspective as well as technological perspective. Every time you let us say you put I mean some instrument out the door, you put some component out the door, some shaft which is used somewhere in an automobile part. You have to specify that failure rate is this is below a certain percentage and so on, and that you can do only if your sample to sample variation is very tiny. Then for with greater level of confidence that the sample you are making is is similar or identical, and you can give that warranty on that sample. So, uniformity is important, again that becomes difficult when you go to the nanoscale. Also this issue of porosity. So, if you are making fine powders, and many times the nanomaterial synthesis process will be easy to do if you are working with fine powders. If your starting point is fine powders, your finishing point is fine powders, things like that, then it is actually easier to relatively easier maybe to get yourself something in the nanocrystalline scale. But the finer the powder you work with, when you do the sintering to make this large scale product, all these issues that we already spoke about, and oxide formation is an issue, but more specifically you can also have porosity. You will have, I mean you will have to do a fair bit of sintering, you will never reach 100% theoretical density, you will start approaching it, but you may have some porosity which will act as a stress concentrator and it will affect properties. So, this is another issue. So, these are all issues when you are trying to make a macroscopic sample which has nanocrystalline microstructure, I mean nanocrystalline structure inside it. Okay. So, nanostructure. Okay. So, one of the techniques that can be used to do this is called a vacuum plasma spray technique. Okay. So, it is part of a set of techniques called the thermal spraying techniques. Okay, so thermal spraying technique, and it is a technique which basically is very large. So, there are commercially available vendors who supply this I mean a machine or instrument that does this process called the vacuum plasma spray process or thermal spray process. So, the chambers are actually kind of large, I mean it is as large as that or is even larger, and inside the chamber you can set up the process that you want, and the samples that you get are samples that you can handle easily, you can handle in your hand and so on. So, the general idea is this, we are using a plasma, and that plasma is generated using a gas and an anode and a cathode, and that plasma is created with and there is an opening through which that plasma escapes from that region where it is created. So, there is a region where the plasma is created and from there it escapes out of that unit through an opening. And if you provide supply of powder at that opening, very close to that opening, that plasma pulls that powder along with it and moves forward. And then you can take and that usually the temperatures reached in the plasma are very high, and then and the velocities generated are very large, we will see that briefly, and then it goes and impinges on some target. In that target the sample is formed. So, this is the basic idea. So, there is a plasma gun which schematically looks something like this. So, you have a system here which is the cathode, and there is another electrode which is the anode. So, we have like that. So, there is an opening in the middle which you can see here. Then there is a small opening here which is connected externally, and it is basically powder supply. They call it the feedstock or things like that. It is this powder that is being supplied to this unit. There is a gas being sent in, that is being sent into this region, and all around this unit, the gas comes in here, and all around this unit you have cooling. This is flowing water, it is not static water, but you have cooling systems. Even here you will have, all around you will have cooling systems. Okay, so, this is all surrounded. So, we are looking at a cross section. So, the water is actually flowing, I am just showing you what will be visible. Then this whole thing is connected up in some sense. So, that is your plasma gun. So, now what happens is you have this powder that is coming down here, and you have this plasma that is being generated, and the plasma goes forward. So, plasma is moving forward and it takes these particles along with it, and the particles melt. As they come out, they are molten, and then one molten set of particles are going with that plasma, and then you have the you have a target here or substrate. On this, the particles that you are sending through the plasma begin to deposit. So, they deposit here. So, this is what the deposit is happening, right. So, this deposit is happening here, and this is the system. So, this is the general system. You can look at there are a lot of detailed images put by various commercial vendors of how their system looks, but in general this is the set of parts that is involved. This is, it says here vacuum right on top, So, what this means is this whole unit that I have just shown you here, which is the substrate, the cathode, the anode, all this supply this powder, everything is sitting inside a big chamber, and the chamber is evacuated. So, first you begin by pumping down the chamber to very low pressure, so that you can remove any presence of air, any presence of moisture from that chamber, and then you refill with some amount of argon, little bit of argon. It is still low pressure, it is filled with little bit of argon, and it is in that atmosphere that you are doing this plasma based deposition process, and this substrate can slowly rotate. So, usually the substrate is in the form of some kind of cylinder, so you keep rotating it. So, this spray will occur on the surface of that substrate, and you can make a reasonably thick spray of a few millimeters thick, and from that you can cut out samples. So, this is the a few millimeters thick, and then a sample that is several centimeters tall and a few millimeters thick. So, that is a sample that you can easily handle and you can do something with. So, that is what we are looking at. So, now what are the some interesting things are there associated with phenomena are there associated with this the plasma spray process. So, the first is this cooling rate. The plasma, by nature of how it is formed, actually attains very high temperatures. You are looking at 10,000 to 15,000 Kelvin. Okay. So, 10,000 to 15,000 Kelvin is the kind of temperature that is attained at the plasma. So, naturally any powder particle that comes there almost instantaneously melts. Okay. So, you will see here that there are some competing phenomena going on, and so we have to be at least conscious of what is going on, so that we can understand why there are some constraints and how you have to work around those constraints. The plasma flame is about 10,000 to 15,000 Kelvin. For your reference, surface of the sun, so surface of the is approximately 6,000 degrees Kelvin, roughly about 6,000 Kelvin is what you are looking at for the surface of the sun. So, therefore, the plasma that you are attaining in your lab is a temperature that is higher than the surface of the sun. Okay. So, that is something that you have to understand. Then the substrate on which the sample is growing, that can also heat up, because you are heating it with something that is at very high temperature. So, invariably that substrate is cooled. So, you need to cool the substrate. To do that, people typically use liquid nitrogen, slowly flowing liquid nitrogen, very small amounts you keep flowing to keep the substrate cooled. So, liquid nitrogen is about we are looking at minus 196 degrees centigrade, or roughly about 70 degrees Kelvin. So, 70 degrees Kelvin is what you are looking at is as the temperature. So, for all practical purposes, you are going from 6,000 Kelvin, you are going from 10,000 Kelvin, which is more than double the temperature of the surface of the sun, from 10,000 to 15,000 Kelvin. So, roughly double the temperature of the surface of the sun. From that temperature to almost 0, in this context, it is going to be roughly the same, whether you go from 6,000 to 70, or you go, whether you go from 12,000 to 70 or you go 12,000 to 0 does not make a big difference. So, you are basically dropping about 12,000 degrees of temperature almost instantaneously. Okay. So, the cooling rates they get are huge. The cooling rates we are looking at is of the order of 10 power 3 to 10 power 5 Kelvin per second. So, you are going from the from a temperature twice that of the temperature of the sun to room temperature in less than 1 second. Okay. So, that is a phenomenal cooling rate. So, this is very important because it is it arrests grain growth. And that is very important, because only if you arrest the grain growth, then correspondingly your nanostructure is maintained. So, whatever nanostructure you want, you maintain. So, it is always a competition between nucleation and growth. So, we want to create a situation here where there is very large amount of nucleation, but a very extremely tiny amount of growth. So, that is the combination that we want to create, and that is what we are doing with this kind of high temperature initially, followed by very fast cooling to very low temperatures. What is the velocity that is attained? Because this plasma is formed, so there is like it is very high temperature, so significant expansion is happening. and then there is vacuum outside. So, it is being pushed out rapidly, it is also being sucked out rapidly because there is vacuum on the outside. So, taking these two into combination, you are usually hitting velocities which are Mach 1 to Mach 3. So, that is higher than the speed of sound, you are going at velocities very high velocities. So, that again shortens the time between where the plasma is formed and that cooling substrate, the cooled substrate. The time taken for particles to traverse this distance is extremely tiny because of this high velocity. Okay. So, one issue that we have is the impact of particle size. So, if you look at, so you can see here that I have indicated that there are there is particle size that we can consider as very small, which is less than 5 microns, less than 5 or 10 microns, and then very large, which is greater than about say 80 microns. So, there are two issues with this, I mean, so corresponding to this there are some issues. So, this is where the particles are coming. So, this is where they are coming out. So, now very small particles, so we will just put here very small, particles implies clogging. The gun can get clogged, the location where those particles are coming can get clogged because the very fine particles will stick to each other and they will just clog the gun. So, it may not necessarily work. Large particles partial melting. So, in other words, if you have large particles, the particles that are coming out of that gun have not completely melted, even though you have because this is where you have to understand the fact that you have now competing processes going on. So, yes, on the one hand you have 10,000 Kelvin, on the other hand you have an 80 micron particle which is now moving at around the speed of sound or maybe even more than the speed of sound and racing towards a target. Once it hits the target, it is going to cool to liquid nitrogen temperature. So, you have a very tiny amount of time during which this particle has to melt and stay molten till it hits the target. So, it is extremely tiny amount of time and even though you are putting 10,000 Kelvin temperature at that region, heat transfer takes some finite amount of time. So, the larger the particle, heat takes certain amount of time to go from the surface of the particle to the center of the particle. So, the larger the particle, the greater is going to be the time required for the heat to reach the center, and so you may not completely melt the particle, and even before that you will hit the target. Okay. And so, if you want to do if you want to change the crystal size, you will not accomplish that if you only have a partially melted particle. If you take an 80 micron particle, let us say it is a single, I mean they are all crystals, maybe just 1 or 2 grains inside that 80 micron particle, then you are looking at say 40 micron, 80 micron crystal size. If it does not melt, then you will still have a residual say 20 micron crystal size, which does not help us. Maybe 20 micron melts and becomes nanostructure because of the sudden cooling, but the other 20 micron has not melted. So, that does not help. So, therefore, partial melting does not help us. Therefore, if you see here, we actually have a range, you have to stay within this range. So, particles used should have sizes say between 10 and 80 microns, 10 micrometer to 80 micrometer. So, this is a size range that we need to have for us to effectively do this process, effectively melt the particle and create these nanostructures. Now, this technique is very interesting because you the microstructure that you create in the sample it sort of has a multi-scale dimension to it, I mean aspect to it, and so we would like to see what this multi-scale microstructure is. We say multi-scale because first there is something called a splat that is formed. So, a splat is I mean it just conveys the idea that something splattered, and that is really what is happening. You are taking a particle, you are taking a particle. So, you have a round particle let us say, and then you have melted it. So, you have some I mean liquidish material with maybe little lower density than the solid. So, it is having little a higher space, and then you have a surface on which it is going to be impacting. So, that is your substrate, right. So, when this particle impacts that surface, you essentially have a splat. It just splatters on that surface, it is called a splat. So, now every drop that is coming forms a splat. So, you have a splat there, you have a splat here, you have a splat on top of it, you have a splat like that and so on. So, you have splat after splat after splat forming on it, and so you usually will have multiple splats. I mean in fact, you have the whole process is full of splats, and those splats are pressed against each other. So, when this is done, if you look carefully in the microscope, you may be able to identify those boundaries, this boundary here, this boundary here, this boundary here, depending on what is visible from the top surface, you may be able to see faintly, you may be able to see boundaries. The nice thing is, so that is one level of the microstructure. So, that may be a largish, so you are looking at a few micron sized splat with a very faint boundary between those splats, but the splat is consisting of nanocrystalline microstructure. So, we will get to that. In between, it is very important that the interface between the splats be oxygen free, only then it forms a nice proper bond between one splat and the other splat. This is accomplished by the fact that we have an argon atmosphere. So, the argon atmosphere helps us ensures prevention of oxidation. Okay. The thing that is happening there is also that you have this molten particle that is coming at very high velocities, like I said Mach 1 to Mach 3, and then goes and hits. So, when one splat forms, even as it is cooling, the next splat comes and hits it. So, you have sort of a sintering going on between splat to splat to splat. That is why you do not have a gap between the splats, they just hit one on top of the other, they sinter with respect to each other, and this is sort of a dynamic sintering that is happening, because one is solidifying, the other hits it, that is also solidifying, so the third one hits it. So, there is it is partially molten, partially solid, and it is all coming together in one place. So, this is dynamic sintering that is going on, and as I said, this is at the larger scale you have the splat. So, larger scale you have these intersplat boundaries. At the smaller scale you have a nanostructure within those splats, you have a nanostructure within those splats. So, this is very useful for us. So, we have now got a substrate here. So, this is the substrate that we had, and on top of this you have got a layer, this layer here which is of this thickness. So, that is the layer that you have got. That layer has splat structure, it has intersplat boundaries which are oxygen oxide free, continuous without any porosity, and it is having a nanostructure. Now, as I said that the substrate can be a fairly large substrate, you can have a pretty large sample as a substrate, because this is a gun which is sitting here and then spraying stuff on it. It is sort of like a sophisticated version of spray painting, but basically you are doing this in a plasma with very high temperatures and some molten material that is coming, and you make this sample. So, the sample is like a thick layer which you can form on top of this substrate, and to the extent that you can maintain the thermal gradient, in other words to the extent that you can keep cooling this sample and you can keep heating it with this plasma, you can make thicker and thicker layers. So, like I said, you can make several millimeter thick layers, and once you have done that, you can carefully machine and remove that layer, and you can remove that layer and you can do various things with that layer. So, if you see here, there is what we spoke about is the general idea of what you can do with this particular kind of technique and the kind of conditions that are required for using it. I am giving you a reference here. It says synthesis of bulk nanostructured aluminum alloy component through vacuum plasma spray technique. This is an ACTA MET paper, so it is a very good journal, and the details are given here. So, you can see here they have actually worked with an aluminum alloy. So, they have worked with an aluminum alloy, which means what? They actually have powder which is now having more than one component. So, you can mix components, you can create the alloy in situ, you do not have to start with an alloy. So, you want aluminum with some percentage of some other component, you take aluminum powder, you take a proportional weight with respect to weight, you take a proportional amount of the other powder, and then you mix them. And so, in the powder supply that you do here, you can actually put the mixed powder. So, the mixed powder can come this way. So, the mixed powder can come this way. So, that will melt and it will go and form a I mean it will melt, it will go and hit the substrate, and so here you will have the alloy. So, you can have a pure material or alloy. So, this can form here. So, what they have done is they have worked with an aluminum alloy and they are able to get bulk nanostructured samples out of it. So, in fact, in their case they actually take a hollow cylinder. So, they take a large hollow cylinder and on the surface of this they make the sample. So, that is how, like I said, you have the cylinder on which you can paint it, and that is how you can flow the liquid nitrogen, etc. So, you get your sample of a certain thickness. So, you get this sample of a certain thickness. So, you are getting like a cylindrical sample on top of a cylindrical substrate, then you can machine it out. So, once you machine it out, you can get various pieces out of it. So, you can radially machine out a whole bunch of pieces. So, you will get sample pieces which look like that. So, this is a fairly large sample, and then you can get radially how many ever based on what your how many degrees you have got here, based on the number of degrees that you have here, you can have some number of samples. So, whatever it is, if you say it is 20 degrees angular dispersion that you have, then potentially you can get about 18 samples out of it, right. So, 18 samples. So, that is a nice thing. So, let us say if 20 degree wide samples, then you have 18 samples. So, please remember, now you have 18 samples made at the same time, and those dimensions could be say anything, So, this dimension like I said, let us say this is I do not know, to give you an example, this could be say 20 centimeters, this could be 0.5 centimeters, so something like that. So, you have 18 samples which are 0.5 centimeter thick, so that is 5 millimeter thick and 20 centimeters long, all of which have been prepared at the same time under the same conditions with the same atmosphere and so on. So, whatever you have generated, you have now got for all practical purposes 18 identical samples of this size, of this fairly large size that I am mentioning here, which is a very significant accomplishment for you to do work where you are doing reproducible samples, where you can study sample behavior with much greater confidence. So, you can make say tensile test samples with this or any other sample that you want to make out of it. You can even make a tool out of it. You want to convert this into some kind of a drill bit. I am just giving you an example of a drill bit. You can make something else out of it, but this is large enough. This is something that you can hold in your hand. You can make a screwdriver out of it, you can make a knife out of it, any number of things which can be made directly out of this sample that you have received. You just have to take it to any industrial production process and you can make this kind of sample. I mean make the product out of it. And as I said, you got this all those problems that I originally mentioned, all the challenges that I originally mentioned are negated in this particular process here. So, surface composition, reactivity is not an issue, you have a argon atmosphere. Boundary between particles is not an issue because you have got very high velocities, and so that splat that forms a very nice boundary between the particles. Uniformity, sample to sample variation should be minimal. Yes, you have got 18 samples here with virtually no variation between samples. Porosity is also virtually non-existent, because again you are hitting molten material on top of molten material, and so some kind of dynamic sintering at very high velocities. It is not, you do not have to put pressure like you would do in the normal sintering process, where you take powder, put pressure and then you do the heating. It is not like that. Here it is arriving hot, it is arriving molten, and the pressure is happening because of the impact of one splat on another splat. So, virtually all these conditions, all the conditions that I mentioned as challenges have been taken care of in this technique. So, they do this with an aluminum alloy, and then they study some mechanical properties, and they are able to show some interesting results based on that. So, if you get a chance, take a look at this reference. So, in summary, there is significant value to directly making a bulk sample that has a nanostructure. We established this very clearly. There is a lot of value both scientifically as well as technologically to making a bulk sample that has nanostructure. The plasma spray technique, which is a part of a type of thermal spray technique, enables you to do this. It enables you synthesis of bulk samples that have nanostructure, and it overcomes many of the challenges associated with other techniques which are starting off with tiny quantities of a nanostructure and then trying to put it together. We spoke of other techniques, we spoke of, let us say, severe plastic deformation. Now, severe plastic deformation, by nature of the fact that you have to deform that sample in multiple times, it is not a sample that can be large scale. I cannot take a big cylinder and keep on trying to deform it in multiple times. The amount of energy that is required to deform that sample is going to be very huge, and I may not have the machinery to do that. So, that is also relatively macroscopic sample. It is not a microscopic sample as opposed to say having a powder sample, but there also I am sort of restricted to thinner dimensions. I maybe have to work with say 2 millimeter thick samples, or some restrictions will be there on what I can do with it, and also the size of the sample in addition to the thickness, and even high pressure torsion. It will be a small sample which has to be held on two sides and then twisted in several different ways. So, you cannot again have 20 centimeter samples, 50 centimeter samples. Those samples you are not going to be able to make in that situation. Even though in many other ways they will meet these requirements that we are talking of. There is no boundaries there, you have better control on the surface, there is no porosity and all that. So, that maybe you can think of it as an intermediate way of in terms of size scale, an intermediate size scale which you can address by using severe plastic deformation kind of techniques. But I mentioned when we spoke about severe plastic deformation that it does have this limitation. Making macroscopic samples, making industrial sized samples is a problem with that. Here you do not have that problem. With vacuum plasma spray technique you can actually make this large scale sample. So, that is a very nice aspect of it. So, those are our highlights for this technique, and I have given you a reference, so please take a look at it, and that is our class for today. We will look at something else in our next class. Thank you.